All right, now we're going to pull together what we've talked about so far in this section. So we'll be analyzing the graph of a polynomial function. So we'll be talking about zeros, multiplicities, and behavior, all that fun stuff. And something that I haven't mentioned before that I just want to point out, you might have noticed when we're looking at these polynomial graphs, even though they all look different, one thing that they have in common is they're all what we call smooth and continuous. So when I say smooth, like an absolute value function would not be smooth because it's got that sharp corner there. So that's not smooth and continuous. Smooth is kind of like curvy. Continuous means you're never lifting your pencil. There's never a gap in your graph. So I just want to point out that fact of polynomial functions. So for the polynomial function f of x equals x times x plus 2 squared, we want to find the following. All right, so first list each real zero and its multiplicity. All right, so for our function, we've got our x plus 2 factor. So if we set x plus 2 equal to 0, that gets us x equals negative 2. And don't forget that x itself is also a factor. So we also need to set x equal to 0. So x equals 0 will be our first 0. And then x plus 2 equals 0 gives us x equals negative 2. So that will be our second 0. Okay. The multiplicity for x equals 0. X equals 0 comes from just that x factor with an exponent of 1. So the multiplicity equals 1, which is obviously odd. So the multiplicity is 1. It's odd. That means it's going to cross the x-axis, behaving like a line. For x equals negative 2, it has the exponent 2. So the multiplicity is 2. That's obviously even. So that means at that point on our graph will touch the x-axis, behaving like a parabola. Okay. So that takes care of A and B. Determine the behavior. We already did that. Okay. D, determine the maximum number of turning points on the graph. This is something else we also haven't talked about, the maximum number of turning points on the graph. So let's take a quick pause. So for the maximum number of turning points, first you need to figure out what the degree of the function is. So in general, if the degree of the function is n, so the degree could be 2, it could be 5, it could be 7, whatever. So whatever the degree of the function is, that means the maximum number of turning points will equal the degree n minus 1, n minus 1, okay? So in our function, for our degree, imagine expanding this out. So we'd have f of x equals, we'd FOIL this out, x plus 2 squared would give us x squared, blah, 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 blah. Then we multiply it by that x out in front. So we would have f of x equals x cubed, and then blah, 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 blah. We don't care about the other terms. So the degree, in our case, is 3, right? The degree of our function is 3. So that means the maximum number of turning points, n minus 1, in our case is 3 minus 1, which gives me 2. So the maximum number of turning points is 2. And when we create our graph, when we take a look at it, we'll talk about what that means. N behavior is like which power function. So we just said that this is similar to y equals x cubed, so y equals x to an odd power. Remember for y equals x cubed, quick and dirty sketch, looks like that. So on the left side falls to the left, on the right side rises to the right. Okay, so we got our maximum number of turning points and we determined the n behavior of the function. Okay, so let's take a look and just see if our predictions came true. And I'll type this in from scratch, y equals x times x plus 2 in parentheses squared. So there's our graph. So let's go ahead and sketch it on our axis here, our xy axis. So first of all, we know we have zeros at, I'm going to use the trace function, at -2. So there's one of our zeros. So -2, 0 is a point on our graph. And 0, 0 is a point on our graph. Okay, so we got those. Boom, boom. Then just filling in some other points using trace. We already have -2, so let's type in, -3 for x, and that gives us -3 for y as well. So -3, -3 is a point. We'll toss in -1. We have -1, -1. Let's do +1. So there's 1, 9. So 7, 8, 9, somewhere up here. And that's probably good enough. Just filling in some additional points. All right, so our end behavior falls to the left, rises to the right. And remember at -2, our x-intercept, -2, 0, it's just going to touch the x-axis and then start heading back down in the other direction like a parabola. So it touches, heads back down to this -1 point, and then at 0, 0, it is going to cross the x-axis, and then it shoots up, and behavior rises to the right, falls to the left. All right, this maximum number of turning points thing. Turning points on the graph. Think about increasing, decreasing, and where it changes from one to the other. So over here to the left, we can see that our graph is increasing until we get to x equals -2. Then it's decreasing. I'm just going to put a D because I don't have a ton of room there, from -2 to -1 on our x-axis. And then it goes back to increasing. Okay, so every time that it changes directions from increasing to decreasing, right there, that's a turning point. From decreasing to increasing, right there, that's a turning point. And then it's increasing farther on. So we can have a maximum number of 2 turning points. Here we have exactly 2. So we could have just had 1 turning point, but we can have at most 2 turning points. Since the degree is 3, we can have at most 2 turning points. Okay, and finally, let's talk about something called the intermediate value theorem. And this is one of those things in math where when you read it, it sounds really scary and intimidating and mathy. But then when you think about it, you're like, oh, well, duh, of course this is true. At least for me. Okay, so the intermediate value theorem. Let f be a polynomial function, smooth and continuous, with real coefficients if f of a and f of b have opposite signs, meaning one is positive, one is negative, then there is at least one value, we can call it c, between a and b, for which f of c equals 0. So I know that sounded cuckoo, but let's just do kind of a quick sketch here. And I'm going to draw something totally weird and crazy, not based on any real function, but okay. So let's say that's our smooth and continuous polynomial function, although none of them would look like that. That looks terrible. All that this is saying is if you identify some x values on your axis, like maybe here's an x value, we'll call that a, and here's an x value, we'll call that b. F of a would be the y value at a, right? F of b would be the y value at b. This y value is positive, this y value is negative, right? So if you've got f of a and f of b on a polynomial function, they have 2 different signs, one's positive and one's negative. That means to get from one to the other, there must be some value c where your function equals 0, so f of c equals 0. To go from positive to negative, you have to cross the x-axis. That's all this is saying. Okay, so to apply the intermediate value theorem, we're given the function f of x equals x cubed minus 2x minus 5, and it says determine whether the polynomial function f of x has a real 0 between 2 and 3 using the intermediate value theorem. So first we find f of 2. Okay, so plugging in to our function here, we'll have 2 raised to the 3rd power minus 2 times, 2 raised to the 3rd power, scoot out of that, minus 2, I'm still in the exponent. 2 raised to the third power, and I'm using the right arrow. There we go. Minus 2 times 2, and then minus 5. So f of 2 equals negative 1. F of 3, 3 raised to the third power. Use that right arrow to get out of the exponent. Minus 2 times 3, and then minus 5 equals 16. All right, so we're trying to figure out if our function has a real zero between 2 and 3 using the intermediate value theorem. F of 2 is negative 1, and that's negative. F of 3 is positive. It's positive 16. So, part C, does f have a 0 in the given interval? Yes. There must be some value, some x value between 2 and 3 for which f of that value equals 0, right? To go from negative to positive, we must be crossing the x-axis. So this is something that will come up in higher level math classes. This is just a quick and dirty introduction right here, but just to show you how that works since we're talking about our polynomial functions.